Hello, my name is Molly Loughney, and this summer in the RISC program, I worked on developing a sensorized glove that could be used to sense the forces experienced by a hand during dynamic motions. As robots become increasingly integrated into everyday life, it becomes important to understand how to incorporate dynamic movements into control models in order to allow robots to move reliably through unpredictable or cluttered environments. We can take inspiration from human motions when considering these challenges and apply facets of them to our control models. Examples of dynamic motions that robots may be required to perform are using walls to change directions, grasping while in motion, or using end effectors to maintain balance. In order to best understand how humans and robots perform these motions, we have developed several methods of measuring the forces applied by hands. These methods include the use of a mounted pressure plate or motion capture data. However, neither of these are adaptable to outside the lab conditions or accessible. To solve these problems, we have developed a force-sensing glove to measure the forces present during dynamic motion tests. Although current research into force-sensing gloves exists, most gloves that are available are either prohibitively expensive or do not measure forces at the required range for dynamic motions. To address this, our glove is developed using accessible materials and is able to sense forces up to 400 newtons, making it ideal for use in studying dynamic motion. Additionally, our glove is adaptable for multiple testing environments, so it can be used to study the dynamic motions of humans as well as those of robots. We designed the glove using FlexiForce A201 sensors, which are force-sensitive resistors. These sensors act as variable resistors which linearly increase in conductance as force is applied. They are integrated into a non-inverting op-amp circuit to improve the linearity of the force versus conductance relationship and are connected to an Adafruit Itsy Bitsy microcontroller to collect the data. In order to determine the specific linear relationship between conductance and force for each sensor, they must be calibrated using a force gauge and the force values related to a conductance value. This calibration process generates a linear equation that can be used to read force directly off of each sensors. The sensors are connected to the glove via Velcro, which allows for an adaptable arrangement of the sensors. There are 4 sensors on the glove, with a standard arrangement having them placed at the index and ring fingers, as well as on the upper palm and ball of the hand. This placement was determined during testing to provide the best distribution of contact across the hand to best represent the forces present. The glove itself is a common latex-free dishwashing glove. Each sensor also employs the use of a puck to evenly distribute force across the sensing surface and away from the sensor edges, ensuring proper sensor operation. We tested a variety of pucks with different levels of compliance to examine how puck compliance levels affect the forces measured by the glove. In testing, we found that the glove acceptably measured the forces during a variety of dynamic motions. We first tested the glove while leaning against a wall, and found that the forces were fairly evenly distributed across the surface of the hand. We found that the hand experiences a maximum force of about 15 to 20 newtons while it is in contact with the wall, and the increase and decrease of that force is nearly instantaneous. We then tested the glove while pushing off from a wall, finding that the hand experienced similar maximum forces to the leaning test. However, we found that the hand reaches its maximum force quicker, and the shape of the graph is more a peak than a square wave, corresponding to the shorter amount of time the hand is in contact with the wall. The last dynamic motion we tested was grabbing an object while in motion. This test displayed similar behavior to the previous 2, except that the forces on the hand decreased slowly after the object was grabbed. We also observed that force was more concentrated in the fingers than the palm. We also tested different sensor movements for the leaning motion and found that more force tended to be concentrated on the palm of the hand, as evidenced by the palm maintaining a maximum force values for a longer period of time. We also found that different levels of puck compliance did not have a significant effect on the maximum force experienced by the hand during the same leaning motion. However, harder pucks did have a higher level of signal noise present in their data than the more compliant ones. These results prove that our glove was able to demonstrate an impressive overview of the forces experienced by a human hand during dynamic motion, with a high level of adaptability and accessibility for future projects. In the future, we would like to concentrate on increasing the precision of the sensor measurements, as we found that on average, the forces reported by the glove sensors were 2 to 5 newtons off for lower force ranges and 10 to 15 newtons off for higher ones, likely due to the limitations in the calibration process. We would also like to continue testing different levels of compliant pucks to determine which is the most well-suited for the uses of dynamic motion, as well as to explore how signal noise is related to puck compliance. Additionally, the circuitry could be adapted to the glove to integrate more force sensors onto the glove, which may provide a better picture of the forces present during dynamic motion. I would like to thank the RIS program, the Robotics Institute at Carnegie Mellon, and my sponsors, the National Science Foundation, for providing me with this opportunity, as well as Rachel Burson, Dr. John Dolan, Dr. Nancy Pollard, and Cornelia Bauer for their support.